All right, so hi everybody. My name is Colin Warren. I'm an undergraduate student from Washington State University, and today I'm going to present to you some research I did on nuclear gas core rockets. So I'm sure if you're anything like myself, when you first saw this topic, you're like, all right, this nuclear gas core, and you're putting rockets. This just doesn't seem like a good idea, or if it is, it seems really dangerous. Today, the intention is, because this was research that was actually done a lot in the 1960s and 1970s from NASA, and then basically a bunch of research from all the white papers I saw stopped after about the 1970s for no reason I could really find. So today I'm hoping to at least bring back and show off this research so that if we, as a humanity decide to, actually can it, it's not for the reason that we don't know about it, but it's because we've looked at it and decided, okay, for all the benefits it have, there might be some consequences as well. So yeah, I'll jump into the motivation first and then talk a bit about some of the other aspects that goes into designing. So the motivation for why you would want to mess with a technology this crazy is primarily can be driven from NASA specifications. There's a 2016 report from the NASA Human Research Program that said with the current state of the art for interplanetary missions, there's an unacceptably high likelihood of permanent injury or death to at least one crew member. That is, if we were to do, interplanetary missions, because, Mars seems to be all the rage today, from their analysis, that the current state of the art they're not really super enthusiastic about it. I'm going to quickly touch on just the chart where they kind of codified and summarized this. I'm not going to go into big detail, but basically all you need to know from this paper is that if you want to go to Mars, you got to look at the bottom of the planetary. And yeah, that's not good. So we want to, if we want to send people to Mars and, in theory, bring them back, as was mentioned, in some of the earlier talks today. What are some of the ways we can mitigate that? So today, I hope to present one idea, which is probably the easiest way, is to just go faster. We go back a couple slides. If you notice, the mission duration, as you shorten the mission duration, your risk tends to go down. So obviously the easiest way is just to go faster. The problem is that, anybody who's familiar with space propulsion in general, is that there's a trade-off between going faster and the efficiency of the system that's making you go faster. And no slide better codifies this than this one, actually presented at an AIAA conference a few years back, actually almost a decade back. Basically has, your rocket efficiency, for those of you who aren't super familiar, the specific impulse off to the left. And then basically on the bottom, your vehicle acceleration or thrust to weight ratio, how quickly you're able to thrust your spacecraft. So you see on the left, some of the technology you saw presented today, kind of the electric propulsion side of things. As you go towards the bottom right over here, kind of the chemical rocket side, those technologies are good for getting you off of Earth, but they're not really efficient. So is there a way we can get the best of both worlds? So that's where we get into this crazy idea. And that is to take uranium, turn it into a gas phase, and then flow propellant around it to get a very high specific thrust or specific impulse and a high thrust to weight ratio. I'll quickly go over just a high level of how it works, and then I'll talk a little more about the details later in this talk. But basically how you do it is you take a uranium rod, you put it, you basically take little fission fragments. If you put enough of them in an area, they'll actually end up starting to, the fission reaction will start interacting in such a way that the particles will start to turn into a gas phase. The gas ends up, because it's uranium in a gas phase, it ends up being really, really hot to the order of 55,000 Kelvin. So then, with that temperature, given that it's going to be, this rocket would end up being a thermal rocket, you end up getting a very high specific impulse and thrust. And then, of course, you have the usual moderators, such as beryllium oxide and deuterium oxide, to kind of keep the criticality of your system going. So before we get into, let's analyze if this is even, like the safety precautions and stuff like that. Is this even worth it? And the conclusion is, yeah, but don't expect a warp drive from this. Here are the performance aspects. You get 2,500 to 7,000 specific impulse seconds. Compare that to some of the stuff that I saw today, where the current nuclear thermal propulsion technology in the solid form is around 900 seconds. Yeah, that's 3 to about 6 to 7 times that performance. Thrust to weight ratio 1 to 5. So that reduces your typical Mars round trip time from about, the current state of the art 7 months to anywhere from 3 to 5 months. But the real question is that, okay, cool, in theory, great, this works, but, we have a lot of speculative technology, like, warp drives and stuff like that. It just doesn't really make sense unless it has a high enough TRL level. Well, funny enough, this technology actually has a lab test of a prototype component or process, which puts it at TRL level 4. And in the next slide, I'm going to show you really quickly, at least the prototype, just really quickly, that's a report that was done in about the 1980s about a ground test they did where they were able to contain uranium hexafluoride in a plasma state. They were able to do it for 120 seconds. This wasn't for a rocket. This was actually for a power generation system, which is another use of this technology. But this at least goes to show that, hey, okay, it's a crazy idea, but we've done this before in a laboratory test. So you can feel free to check out at least this paper down below for more details. Not a whole lot, because my intuition is that there might be a fair amount of it that's classified, not a whole lot of details. But there was reports showing that they were able to do a technology like this successfully. So given, okay, if I've convinced you that there's a motivation for it and the solution to the motivation is worthwhile enough to pursue it, let's check out, okay, what's the current research, other entrance applications, but most important of all, is it safe? So let's go in first into the safety considerations and see if we have solutions to mitigate those various aspects. So the 3 top things you're going to have to worry about if you're doing something like a nuclear gas core, nuclear in general, is the environmental concerns. If there's an explosion on the launch pad and you wanted to decrease, you want to decrease proliferation or making sure that people who don't want to get nuclear weapons don't get nuclear weapons. So we'll jump into the first one of these, the environmental concerns for testing. Basically, all of these problems can be solved. But 2 things. One, if we turn the nuclear core gaseous, we want to make sure we either do it in a certified testing facility where if things go wrong, we can contain it, mitigate the risk. There's currently, facilities that exist for that. As you saw previously, they did testing for this. So there are facilities that have existed in the past where they are able to do it successfully. And, we haven't heard horror stories about it yet. Or if we end up, using it in the field, you don't turn the core into a gas phase until you're in a nuclear safe orbit, which basically means, okay, you're in a trajectory, you're out of Earth orbit, you probably use solid or liquid propellant to get it off of Earth. And then from there, once your trajectory is such that you're never going to re-enter Earth and you get all those fun radioactive particles, you have to explain to your constituents about why there's radioactive waste falling from the sky. If you put it in orbit where you don't have to worry about that, then you can turn it on and get the performance aspects that you want from here. So next thing, really quickly, the explosion on a launch pad. Again, this can be mitigated by keeping the core when it's on the launch pad solid and not turning into a gas phase until you get into orbit. You can kind of think of it as you're not lighting the candle of the nuclear stage until you're out of Earth's orbit. The nice thing about keeping it in the solid core stage, at least while on Earth, when you're transporting it, is that there's been a lot of safety precautions put into place because there's been a lot of research done in the 70s and 80s and recently, as NASA's gotten a re-interest in nuclear thermal propulsion technologies, about launching rockets with the solid core stays. The best example, of course, is the very fun Kiwi nuclear test done in 1965, where they basically wanted to see, hey, they did some theoretical analysis to say, okay, if we have this core, when we blow up on the launch pad, it shouldn't turn into a thermonuclear explosion, but just to really illustrate to people that this isn't going to happen. They ended up doing that. They took a core, put it on the launch pad, blew it up, and they ended up showing that, okay, there was an explosion, of course, but it had to be a conventional one, not a nuclear one. How far the blast damage went to 1,000 feet. So obviously, if you're blowing it up, don't take selfies really close near it, stand back. And then the contamination levels that came from the test lasted only about a few hours. They lasted about, the actual dose levels was about 1 milligram per hour. You can think of that for those of you kind of like myself who aren't familiar with, okay, what does that mean? How does that relate to my everyday life? 1 milligram is about the dose you get from a trans-American flight from Seattle to New York. So if you think you get, okay, that's about the radiation dose you get every hour for up to a few hours, and you don't get that dose, from what they found was really hard to find about 2 miles away, and they couldn't find it all past 12 miles. So if you're doing your own launch designs and stuff like that, you can put in your own safety precautions. That's what they found. And there was another fun story where, this was obviously not PETA approved and it was the 60s. So, I guess you could do stuff like this. There ended up being cows downwind of the test. Don't ask me the details about that. At least in the paper that they wrote up on this, they ended up actually taking milk samples from the cows, and then they showed that, hey, and if you took the milk, there wasn't actually detectable fission products in the cow's milk downwind from the test. So that's also something nice too. If you end up drinking milk down from a place where they're testing rockets, because that's your thing. But yeah, so explosion on the launch pad, as long as you keep it in a solid form, we have ways to mitigate that. Finally, non-proliferation. Again, this is mostly, for those of you familiar with the nuclear side of things, this is something that's mostly addressed by the refinement of uranium, because the hard part for making bombs is not actually making the bomb, it's getting the uranium to make the bomb. So at least in terms of, researchers end up being interested in pursuing this, there's not too much we can do with that, because most of it, the non-proliferation side of things, is in the refinement side. But if we want to do our part, as long as you keep the enrichment levels of the uranium you're testing with to 20% or less, that significantly reduces the risk of bad actors taking those rods and turning into weapons. It also makes it a lot cheaper because you don't have to go through as many regulatory steps to make it happen. So if I've convinced you that, okay, there's a motivation, here's the solution to the motivation, and it's safe, or at least we have safety precautions in place. I'm just going to quickly go over the really high-level research of what's here. Again, at least the paper I put in, it went into really big detail. I'm not going to go super big detail. It's mostly going to be a very broad overview about what things you can look forward to if you went into researching this. But yeah, we'll get started with the first thing, and that is the two different designs for nuclear gas core rockets. There's two different ways you can do it. Because again, as you remember, if we have the fissioning uranium core and the gas phase in the middle, you have to keep it there somehow. There's two ways of doing this, and both are very fun. The first way to do it is you end up taking a propellant, because you'd be flowing around your hydrogen propellant to heat it and throw it out the back. You end up actually creating a vortex with that propellant, and you end up using the vortex such that it contains the uranium inside of that vortex, and the uranium conductively and radiatively heats the propellant going around it. Obviously, if you're a researcher looking for a fun fluid dynamic problem, a lot of great interesting areas there. The other way to do it, which actually mitigates one of the primary problems with the open cycle, is the closed cycle design, which basically you take your fission uranium, you put it in a glass quartz wall. Instead of conduction heating your propellant, you end up having radiation coming from your fissioning gas core, and that radiative transfer ends up transferring the heat to your propellant. The reason why you would choose open cycle versus closed cycle is that, as you can imagine, if you're doing fluid vortexes, you end up getting a little bit of fuel loss, because even if you come up with pretty good confinement mechanisms using vortexes, still not perfect. So the closed cycle ends up mitigating this problem. The problem is you end up having a specific impulse loss. Where the closed cycle, you get a max specific impulse around 2,500, whereas the open cycle ends up being around 7,000. So yeah, that's something to consider when you're looking at different ways of approaching this concept. A little bit more about different lab tests they did, really high level. In terms of the vortex, there's two different ways that they looked into confining plasma. One, of course, is the hydrodynamic confinement, where you did the vortexes. They haven't actually done, actual outside of the 1979 test. They didn't do any ones for rockets specifically, but there was actually some NASA research that looked into using smoky air and inert gases like freon or argon, and seeing if you could contain one using the other using vortex methods. As you see on the picture on the right, here's a lab test from that. They show that, hey, you could do this. They were able to codify some of the design parameters. So they end up saying, hey, this is promising. There's some problem areas, but here's some solutions to this. So that's for the vortex hydrodynamic confinement. The other area that's largely unexplored is the magnetic field confinement, because again, you're working with a plasma, so you have magnetic fields at your fingertips to confine it. There's not a whole lot of research into the magnetic field side, because there's the initial paper that came out looking at this ended up in the abstract saying, hey, it doesn't look promising. So I think that's ends up being why a lot of people didn't go down this route. The problem is if you actually look in the paper and you look at the very end, they ended up looking at some of the results and said, hey, it doesn't look promising, but we're comparing our models to just some general fundamental physics. And it seems like we're saying things about physics that don't seem to work. So it might end up being promising. But yeah, at least this model doesn't seem to show it that's necessarily working. There needs to be further research. Later, some people at MIT showed, hey, there's some promising areas from it. But yeah, both of these areas very largely unexplored. Yeah, so that's the confinement. Heat transfer, a little bit about that. Again, as you have a fissioning uranium core that's in the plasma, you can kind of think of it as like a mini sun that you have going on, inside of your combustion chambers. So there's going to be, some radiative heat transfer there in addition to conduction. In terms of the specific wavelengths that you're looking at, initially when they built some of the models, they were expecting, okay, from the theory that we're predicting, we're looking at the radiative transfer, we're expecting, okay, after about the ultraviolet and lower wavelengths, we should see there shouldn't be as much radiation being emitted in these wavelengths, so we should design a propellant around the ultraviolet and higher wavelengths. Well, when they end up doing some of the shock tube experiments, they found the complete opposite, where they ended up finding most of the radiation that was emitted from these balls of plasma ended up being in the ultraviolet and lower ranges. So, that was an interesting surprise. I couldn't speak to the details about, why they found their theory diverged so much from their experiment, but that was a nice little surprise. And it ended up manifesting to the point where okay, you have your hydrogen going around, but one thing that they noticed is that, okay, the hydrogen isn't absorbing as much of that thermal radiation at those lower temperatures. So one thing they came up with, and something that they're actually looking into today for solid cores, that's actually taken a lot from this gaseous core research, is that if you seed your propellant, your hydrogen propellant with little tungsten seeds, you end up actually transferring more of that heat radiatively. And even though you get a bit of a specific impulse decrease, you end up getting you get a bit more thrust because you have more particles going in there, and you just get better overall heat transfer characteristics. One other thing about the heat transfer, again, at lower temperatures, they found for propellants like hydrogen, there wasn't the absorption from hydrogen was great, but not super, super great. But what they did find is that as the temperature of the propellant went up, the absorption coefficient of hydrogen ended up actually increasing, which is obviously pretty good because you have, you're going to be heating your gaseous core ball is going to be, tens of thousands of degrees. So if you have your fuel absorbing more of that radiation, that's obviously a very good thing. So to quickly wrap up, just give you some quick next steps. Again, we showed you, okay, these are kind of the areas. If you're designing one of these systems, here's what some of the previous research that was done in the 60s and 70s that hasn't really seen a whole lot of people working on it till now. So I've managed to convince you that, hey, there's a motivation for it. This solution is a very good solution to it. There's a way to do it safely. Here's some of the previous research. And you're like, all right, I'm a researcher. I want to go and maybe try to help advance this area a bit. There's a lot of areas that are untapped that you can explore as someone who's looking for a PhD. Again, most of these models were made in a day when they didn't have FEA tools. So there's a lot of areas for computers to go in and do a lot of simulations, do some updated engineering designs. You can just, if you're a PhD student looking for something interesting, there's so many papers that you could just basically take from the 1970s for this technology and then just update it from there. So yeah, and then I touched on it a little bit briefly, but again, if you're looking at more kind of a motivation for why you would also want to fund this research outside of you want to go to Mars because you want people to not die as likely, is that there's some research done from the one symposium that did on uranium plasmas, some applications for power generation and gas lasers and some other areas of basic research. So here's the white paper if you want to go check that out. So thank you very much. My name is Colin Warren. Hope you enjoyed my presentation on a concept that hasn't really been, NASA developed a lot in the 1970s and kind of went underground. So hopefully today, so we'll see if I convinced anybody or at least got some interest in it. I want to give a special thank you to David Koch, who was kind of the guy reading all my paper, just, helping me sort out the different areas, the areas I was a little bit more weak in from the nuclear, helping point that out. I'll give a special shout out to Ritz Rahu and Dr. John Foster from the University of Michigan for, one, taking my unsolicited emails just asking about this technology, because they're the only two researchers I could find that are working on this. So somebody's in the funding department is interested in this technology, give them more funding. And then I want to give a special thank out to Dr. Hutz from NASA, and a special shout out to my mom because she's pretty awesome. So yeah, thank you, and I'll take any questions.
Thank you, Colin, for this great presentation. Love the enthusiasm.
I tried my best. Thanks.
Okay. All right. I'll hand over to our judges for questions and feedback.
Hey, Colin, this is Ethel. I just wanted to say this was a really well-rounded presentation. I really enjoyed how you presented the research, but I did want to ask, in the future, I'm assuming you want to go into nuclear gas rockets, but I wanted to know if you wanted to propose a different design and how to do it, or continue on with the research that was done before, if you wanted to put like your own little twist into it.
Yeah, off the top of my head, I didn't really look into, okay, if I were to take this design, how I go about tweaking it. Most of my main focus for this one was mostly to go, okay, I want to find all the relevant research that's been done up to this point, put into one document for anybody who's interested in, kind of reviving this sort of research. But yeah, in terms of my ideas about how I would tweak it, other than, the suggestions that I've found that I kind of touched on today in these papers and in the big white paper, yeah, nothing more off the top of my head. Yeah, that's my answer for that.
Okay, sounds good. Yeah, I just wanted to see, because it is a very interesting subject, but I wanted to see if during your research you found like little things, or like, oh, it could be better if we did this, or yeah, just different things. But yeah, it was a really good presentation. Thanks.
Yeah, thank you.
Hey, Colin, this is Ariana. Yeah, I just wanted to second everyone's comments. I think you're a fantastic communicator, and I think there was a great engagement with the room, so definitely wouldn't tell you to stop doing that. I would like to mention some comments, though. I think, you did jump in quite quickly, and though it was engaging, I would have kind of liked more of an outline of what I was going to see, moving forward. So another thing, I saw that you had TRL in one of the slides, but I just didn't see, that definition anywhere. And I understand, I know what TRL is, and you do, and I'm sure other people do, but it's always safe to never assume. So just define your acronyms.
Yeah, fair enough.
And then, yeah, no worries though. And then I think it was a really great presentation, a lot of great content. It was a little high level for me, I guess. Maybe in this setting, in this research presentation setting, I would have liked more details. I know the devil's in the details, and I know you said you had a lot. And it's hard to. We've been in these. We've been listening to these presentations, and you can never have too many, but you can never have too little. It's really that what was it? That perfect blend. But I would have definitely liked a little bit more data. And yeah, overall, I think it was a pretty great presentation. So great job.
Yeah, no problem. Yeah, at least that was one of the decisions I know I had to make, because one of the intents for this talk was to, okay, primary purpose is to convince people that, this technology exists and it's safe enough, but yeah, something else too which is why I think referring to people to the white paper is probably the best place, because that's where I have a lot more of the details that I couldn't quite cover in this talk. But yeah, if I had more time, I could go on long rambling tangents on all that fun stuff. But yeah, fair enough.
Hey, Colin, this is Elliot, judge number 3. So I just had a couple of questions for you. So the first question I had was, I saw in one of your slides you had an unexplored method of confinement with the fission reaction was a magnetic field, but I know that at least in fusion reactor prototypes, they use I think there's a few different flavors of them, but an example that just comes off the top of my head is a tokamak, kind of designed to sort of give you that magnetic field so that you can build up your temperature and not melt your system. Is this something that you came across in your paper as maybe a repurposing? I know it's a different type of nuclear reaction than fission, what you're talking about here, but is that something that you came across in your research as maybe a modifiable way of confining it?
Yeah, absolutely. Because obviously, when you talk about tokamak, you have, the magnetic field confinement fusion. You have, the laser confinement fusion, or at least in the inertial approaches. This particular one, you could take a lot of research that's done in kind of the more nuclear fusion side, and you could definitely apply it towards, okay, you're taking fission products that are in a fissioning gas state. I didn't look into that area in particular, because I think, that area, I think you could probably write a few, PhD theses on, hey, I'm taking all the work that they did with the tokamak, and now I'm fusing it with this interesting area. And then here are all the details that fall out from kind of fusing these two fields. But that's definitely an area where, we have all this research going into, less crazy radioactive worries areas that you could potentially bring in. That's one thing in the back of my head that is like, okay, you can look at it, but I didn't go too deep into the details on that.
Okay, fair enough. And then my other question was, so if you have, a fission reactor that's generating some, rocket exhaust, I was just kind of wondering, and I didn't see it cited in the presentation, but maybe I need to redo my LASIK. What are the products of fission in the exhaust? Is there anything that would, because I know one of your concerns, and by the way, I want to commend you on citing environmental concerns in this presentation, and it seems like you kind of took a holistic approach to this whole thing in terms of sort of, what is the risk and all that. But I just wanted to ask if you had come across that in your research. Is there any fission products that in the exhaust that you would think would be an environmental hazard?
Yeah, off the top of my head, this is also why I wrote the paper, because I always have to go back and read the white papers on it. Touching a little bit on that, I don't remember this particular isotopes. I think one of them was some form of iodine. Don't quote me on that though. But I know in terms of how they plan to mitigate, capturing those, because this is something that they end up having to do for those radioactive waste products that's used a lot in the nuclear industry, is that they have a lot of wet, at least on the third bullet point, they have a lot of wet electrostatic precipitators that can kind of pull off some of those radioactive products, in addition to doing your usual, lead shielding, confinement mechanism, in addition to putting it in an area that's not super geologically active. Those are the sort of mitigation techniques, or just a small sampling. This is another PhD thesis probably waiting right here, of different things you can do to make sure whatever radioactive waste products you have come out, that, how you capture them and how you safely store them. Because that was the main thing, especially when I saw this concept, is like, all right, I could talk about the details, but if you're soliciting funding, I'm sure the first concern everyone's going to have is, all right, so we're usually worried about reactors melting down, and now you're purposely suggesting we melt them down to turn into a rocket. Why? So I wanted to make, here's the reason why you want to develop this technology. Number two, it's safe. That high level look, in terms of the original question, I don't remember the actual radioactive waste products off the top of my head, but here are some of the different technologies they have for capturing and storing them.
Okay. Yes. Other than that, just I love the energy of the presentation, and it definitely I was very interested in what you were saying the entire time, and in terms of convincing me that I need to look more into this field, or at least pay attention to it. I think you've succeeded on that front. So
right.
Good job overall.
Got one. Perfect. I guess in the 2 minutes I have left, any other wild random questions from the audience? Awesome. I guess that makes our job easy, Ian.
It sure is.